Good day everyone and welcome back to our YouTube tutorial. We know that basic calculus is a little bit difficult and confusing, but watching this video will hopefully help you to understand the different concepts of the subject. For today's video, we are going to discuss the 20 equations of the table of integrals with examples. In this lesson about antiderivative and using U-Substitution, we are first going to know what it is all about.
Integration is the process of finding the function of a derivative. Since there will be some equations that are difficult to integrate directly, therefore, there is a method used which is called U-Substitution. The U-Substitution is a method that is used in order to help us integrate composite functions or functions which are written inside another function. It is said that this method could be called as the counterpart to the chain rule, thus being called the reverse chain rule. Since you have already learned the meaning of the lesson, let us now show you examples of antiderivative.
Equation 1. Integral of dx equals x plus c. A simple example is the integral of 10x dx, which is equal to 10x plus c. Since we only need the constant plus the arbitrary variable c. In equation 2, integral of x raised to n dx is equal to x raised to n plus 1 over n plus 1 plus c. If n is not equal to 1, here the example given is integral of 30x squared dx. First, we have to move the constant 30 before the integral sign, then leave x squared as our of u. Then do the anti-differentiation. We have x raised to 2 plus 1 over 2 plus 1. It will be x cubed over 3 combine both terms. We'll have 30x cubed over 3 lowest term. It will be 10x cubed plus c. Equation 3. Integral of constant a f sub x dx equals constant of a integral of f sub x dx. Here we can have an integral 15x times the quantity of 3x squared plus 1 all over 2 dx. First thing to do is to put the constant 15 before the integral sign. Then 15 times the integral of x times the quantity of 3x squared plus 1 all over 2 dx. Let u be the inside function of 3x squared plus 1. We will have 15 times the integral of u squared over 6 du. Move the 1 over 6 beside the constant 15 to leave the u squared du after the integral sign. Next is to do the anti-differentiation. U raised to 2 plus 1 over 2 plus 1, we will have the 15 times 1 over 6 times the value of u, which is quantity of 3x squared plus 1 raised to 2 plus 1 over 2 plus 1. Multiply 15 and 1 over 6 and 3 will get 5 over 6 times the quantity of 3x squared plus 1 all over 3 plus c.
Integral of the quantity of f of x plus or minus g of x dx is equal to the integral of f of x dx plus or minus g of x dx. An example is the x times square root of x plus 5 dx. Our u will be the inside function of x plus 5, du is equal to dx. Since our u value is not the same as the x variable, what we need to do is to add the negative 5 on both sides and to the u is equal to x plus 5. So it will be u minus 5 is equal to x. Then we'll have an integral of the quantity of u minus 5 times the square root of u du. Since we can change the square root of u into fraction, we'll have the integral of the quantity u minus 5 times u raised to 1/2 du. Then distribute, it will be u raised to 3 over 2 minus 5u raised to 1 over 2 du. Then get the antiderivative, u raised to 5 over 2 over 5 over 2 minus 5u raised to 3 over 2 over 3 over 2 plus c. Lastly, reciprocal the denominators to move it to the front. Then get the original value of u, which is x plus 5. The final answer will be 2 over 5 u raised to 5 over 2 minus 10 over 3. Since we multiplied 5 to 2 over 3, so 10 over 3 x plus 5 raised to 3 over 2 plus c. Lastly, reciprocal the denominators to move it to the front. Then get the original value of the u, which is x plus 5. The final answer will be 2 over 5u raised to 5 over 2 minus 10 over 3. Since we multiplied 5 to 2 over 3, so 10 over 3 times x plus 5 raised to 3 over 2 plus c. Integral of e, or the Euler's number, dx equals to e plus c. An example of this is the integral of x times the Euler number raised to x squared dx. First thing to do is to apply the U-Substitution method, in which the equation will be integral of e raised to u all over du, and we'll have the value of u as x squared. Then take the constant out of the equation and it will be 1 over 2 multiplied by the integral of e raised to u du. Once we're done taking the constant out, we will be using the common integral that will give us 1 over 2 e raised to u. Substitute back the value of u and add the constant c to the expression, and it will give us an answer of 1 over 2 e raised to x raised to 2 plus c. Integral of constant a raised to x dx equals to a raised to x all over the natural logarithm of a plus c. A simple example is the integral of 2 raised to x, which is equal to 2 raised to x all over the natural logarithm of 2 plus c. Since we only need to substitute all the values in the given equation, we'll get 2 raised to x all over the natural logarithm of 2 plus the arbitrary variable c.
The number 7 in the table of integral is the x raised to negative 1 dx equals the integral of 1 over x minus natural log of the absolute value of x plus c. Here we can have the integral of 2x cubed plus 5x over x to the 5th plus 6x squared. First thing to do is to remove the fraction, then place the denominator beside the first term. That is why we will get the integral of the quantity of 2x cubed plus 5x times the quantity of x to the 5th plus 6x squared all over minus 1 dx. Our u will be x to the 5th plus 6x squared. Getting du, we will have 5x to the 4th plus 12x. du is equal to 5x to the 4th plus 12x, and dx is equal to 2 times 2x cubed plus 5x dx. Then move the constant 2 before the equal sign. It will be 1/2 du is equal to 2 to the cube plus 5x dx. Then the integral of the quantity of 2x cubed plus 5x times the quantity of x to the 5th plus 6x squared raised to negative 1 dx is 1/2 integral of u raised to negative 1 du, which will be equal to 1/2 natural log of the absolute value of x plus c. Our final answer will be 1/2 natural log of the absolute value of x to the 5th plus 6x squared plus c. The 8th integral given in the table is the integral of sine x dx equals negative cosine x plus c. An example for this is integral of x sine of x squared plus 7 dx. First thing to do is to apply the U-Substitution method. What we need to do is to get the derivative of x squared plus 7, which will only be 2x. And then divide 2 both sides to leave x together with dx. Next, take out the constant out and it will be 1/2 multiplied by the integral of sine of u. Since we all know that in sine x, it will always be negative cosine x. So our final answer will be negative 1/2 cosine times the quantity of x squared plus 7 plus c, since we have to take back the original inside function from the U-Substitution. Next is the 9th on the table of integrals. It is the integral of cosine x dx is equal to sine x plus c. For example, we have the integral of cosine times 6x dx. Our u will be 6x. Getting the derivative, it will only be 6. Then divide the 6 both sides of du and dx. We will have du over 6 is equal to dx. Now, we have the integral of 1 over 6 cos u du. Make cosine to be a sine. Now it is integral of 1 over 6 sine u plus c. Lastly, take the original inside function 6x from the U-Substitution. Our final answer will be 1 over 6 sine times 6x plus c.
Now let us have an example for the integral of secant raised to 2x dx. The integral of secant squared times x cubed times 5x to the 4th power. Here, we can have our u as the inside function, x cubed du. Getting the final answer, we must remember that secant's opposite is a tangent, so our final answer will be tangent times x cubed plus c. For the 11th list on the table, it is integral of the cosecant raised by 2 dx. Our example will be the integral of cosecant squared times x raised by 7 times 7x raised by 6 dx. Just like equation 10, we'll just get the inside function, which is x raised by 7. Get the opposite of cosecant, which is negative cotangent. So our final answer will be negative cotangent multiplied by x raised to 7 plus c. Let's move forward with the 12th integral list on the table. Integral of secant of x tangent of x dx is equal to secant of x plus c. Here we can have our example as an integral of 2 secant x4 tangent of x dx. First thing to do is to take the constant out of the expression, and it will give us 2 multiplied by 4 multiplied by the integral of the secant of x tangent of x dx. Then simplify the constants by multiplying 2 and 4, which will give us an answer of 8. Once we're done simplifying, apply the U-Substitution method, wherein we would get the value of u as secant of x and an expression of 8 multiplied by the integral of 1 du. And by applying the constant rule, we will get an expression of 8u. Last thing to do is to substitute back the value of u and add the constant c to the expression, which will give us a final answer of 8 secant of x plus c.
For the cosecant x cotangent x dx, our example is the integral of cosecant x raised to 10 cotangent x raised to 17, 18x raised to 7 dx. For the solution, we have to use the U-Substitution method, where first we will have to get the u, which is almost always the inside function. Therefore, our u will be x raised to 10. Then we have to get the opposite of cosecant x cotangent x, which is negative cosecant. Then our final answer will become negative cosecant x raised to 10 plus c. 14th on the list, we have the integral of tan x dx. So our example in this equation will be the integral of tan 36x raised to 4 18x dx. So the first step is we will have to get the u, or the inside function, which is 36x raised to 4. Then we will have to get the opposite of tan, which will always be the negative natural logarithm of the absolute value of cosine u plus c. So now we can substitute and get our final answer, which will be negative natural logarithm of the absolute value of cosine 36x raised to 4 plus c. For the 15th example on the table, which is the cotangent of x dx equals to the natural logarithm of an absolute value of sine of x plus c. Our example for this will be the integral of 2 cotangent 2x dx. What you need to do first is to take the constant out of the expression, which will give us 2 integral of cotangent of 2x dx. Then expand and transform the expression inside the integral, and we'll be having 2 multiplied by the integral of cosine of 2x all over sine of 2x dx. Now we can apply the U-Substitution, and it will give us a value of u as sine 2x and an expression of 2 multiplied by the integral of 1 over 2u du. Next thing to do is to take the constant of the inner part of the expression, which is 1/2, and we will have 2 multiplied by 1/2 multiplied by the integral of 1 over u du. By using the common integral, we can derive our answer as 2 multiplied by 1/2 natural logarithm of an absolute value of u. Then substitute back to the value of u and further simplify the expression and add a constant of c, for us to have a final answer of the natural logarithm of an absolute value of sine 2x plus c.
The integral of secant x dx. An example is the integral of secant quantity 17x raised to 3, quantity 87x raised to 5 dx. For the solution, we will have our u as the 17x raised to 3 du. Then, remember that in secant x dx, the answer will always be natural logarithms of the absolute value of the secant u plus tangent u plus c. Our final answer will be the natural logarithms of the absolute value of the secant 17x raised to 3 plus tangent 17x raised to 3 plus c. Integral of cosecant dx equals to natural logarithm of an absolute value of cosecant of x plus tangent cotangent of x plus c is our 17th integral list on the table. As for our example, we have an integral of 2 cosecant of 2x dx. First thing to do is to take the constant out of the expression, and it will become 2 multiplied by the integral of the cosecant of 2x dx. Then apply the U-Substitution method, which will give us a cosecant of 2x plus cotangent of 2x as the value of our u, and 2 multiplied by the integral of 1 over u du for our expression. With the use of a common integral, our expression will become 2 natural logarithms of an absolute value of u. Lastly, substitute back the value of u to our expression and the constant c, which will give us a final answer of 2 natural logarithms of an absolute value of cosecant of 2x plus cotangent of 2x plus c. For the third to the last list on the table, the integral of dx over the square root of a squared minus x squared. A simple example of this is the integral of 1 over square root of 7 minus x squared dx. When we have this kind of problem, always remember that we need to put negative 1 to any of the sin, cos, tan. For this example, we have to put arcsin quantity x over 8. Here, we have arcsin quantity x over square root of 7. Rationalizing, we will have arcsin square root of 7x over 7 plus c, which will serve as our final answer. For the second to the last list on the table, dx over a squared plus x squared. Example is the integral of 1 over 49 plus x squared dx. Our u will be the x over 7 raised to 2. Take the 1 over 7 from 1 over 9 over 49 before the integral sign. Now we have 1 over 7 integral of 1 over 1 plus u squared du. Next to do is to include arctan. It will be 1 over 7 integral of arctan u plus c. The final answer will be 1 over 7 arctan quantity x over 7 plus c.
And the last on the list, dx over x times the square root of x squared minus a squared. The example can be 1 over x times the square root of x squared minus 1 over 100. First thing to do is to make 1 over 100 be 1 over 10 raised to 2. Then we will have 1 over 1 over 10, since 1 over 10 is still the denominator of 1 times secant of 1 over 1 over 10. To get the final answer, we have to include the arcsecond, which will be 10 arcsecond 10x plus c.
And that is all for this math tutorial. We hope that you learned something new. Don't forget to hit the like, subscribe, and click the notification bell for more updates. See you in our next video. Bye!